Previously, I banefully botched a batch of snickerdoodles. I dare not speak of the culinary sin committed, but I did correctly create a second batch of cookies, coloring them a morose mauve in memoriam of their muted mates. I brought them to a scurrying soiree, along with a few other meticulously manufactured morsels, and inquired how it affected spirits using a stellar assessment system. However, I was hopelessly hexed with the dearth of data. 6 intertwined responses decreeing that the carelessly crafted cookies were better than the other ones. Though, a statistical test did not reach an absolute verdict. I could not differentiate without doubt which was worse. What I need is more power. Statistical power. A powerful statistical test is, as the name suggests, and to my delight, more powerful. What that means is you have a greater chance of separating signal from noise, seeing truth among chaos, and, more formally, rejecting a null hypothesis if it is indeed false. My null hypothesis, as it was that my mistake would not make the snickerdoodles less satisfying to eat, and the alternative hypothesis, which is what I actually suspected, was that it did. Theoretically manifested by their star rating being lower than the dark purple ones for any given person, on average. Of course, tomorrow night is another night, and snickerdoodles can be summoned up quite efficiently. I could bake more, but how many would I need? How many would I need to be certain of a difference? Ideally, I would have at least an 80% chance of achieving an answer using a 5% significance level. But first, we should decide what kind of difference we would like to identify. Firstly, if we want to see if there's any difference between the two cookies, we should define what a minimum absolute difference between the two should be. If, for example, they were only rated 1,000th of a star apart on average, it would take a factory's annual output worth of cookies to identify a difference. Before, the difference was 1/3 of a star across 6 surveys, and that seems like a reasonable difference to use. Then, we should guesstimate what the standard deviation of the ratings differences should be in that scenario. In my sample of 6, there's a sample standard deviation of 1.37. But, as that is not a lot of data, the actual standard deviation could be quite higher. And to make things more complicated, since the maximum difference is 4 stars, between a 1-star rating and a 5-star rating, it's not so easy to come up with a good range of possibilities and their probabilities. Without going into too many details, I came up with a rough estimate of what the probability distribution of the variance might be, and used that to simulate the possible experiments. We can see the possible outcomes of this graph here. There are 2 dashed bars indicating 80% power and 90% power, common thresholds used when designing experiments. Starting with the green bar, in the scenario that our standard deviation is 1 star, we have sample sizes of 143 and 190 for the suggested sample sizes. If the true standard deviation is equal to our estimate, then we have a sample sizes of 265 and 354 for 80 and 90% power, respectively. And for what I consider a reasonably likely worst-case scenario of a standard deviation of 2, we need a size of 566 for 80% power, and, though not listed, 758 for 90% power. Considering there is uncertainty in our standard deviation, my simulation suggested that a sample size of 194 or 265 for 80 and 90% power respectively would be reasonable, which is about halfway between the sample size of our estimate and the case where our standard deviation is 1. Additionally, if you're looking at different effect sizes, this is what the power looks like across sample sizes if the standard deviation is actually 1. The yellow region is basically guaranteed to find a significant effect, while the dark blue region is very low, and the pinkish region being somewhere in the middle. If we wanted to calculate how many cookies I need to bake, all we need to do is double the sample size, since each sample consists of 2 cookies being eaten, although I would have to bake even more, considering people tend to eat more than 1 each. I would already run into an issue of having enough test subjects to easily find for such a study. On top of that, the ingredient cost would not be too trivial. Of course, cookies can be made in different sizes, but let's say a single recipe batch yields 30 cookies. Using the recipe I found online, Grandma Ruth's Easy Snickerdoodles. 1.5 cups of white sugar, 1 cup of butter, 2 eggs, and 2 3/4 cups of flour. And these other ingredients that are far more trivial in quantity and cost, namely salt, cream of tartar, and baking soda. And the cinnamon in the coating, which I grind from a large quantity of sticks I've had for a while, and the food dye, which doesn't need to be used too much. Considering the quantities at hand, I'll use wholesale or otherwise large quantity prices for the following ingredients. Sugar, 30 cents per cup. Butter, $2 per cup. Eggs, prices that rise to the heavens and fall to the ground. But $3 a dozen sounds sound. Flour, for all purposes, 15 cents per cup. This would mean that it costs about $3.36 to make a batch, or $7.72 for a pair of batches. I would be spending about $50 to $100 depending on how many batches of cookies I wanted to make, possibly double to account for people eating more than one of each. There are other ways of analyzing data though, and even though a paired t-test is quite straightforward in answering the question, is one rated higher than the other, I think my oven deserves some respite. And yes, for those of you shouting at your screens, there is nuance in interpreting the rejection of a null hypothesis. It surprisingly tells us very little in reality. For example, we are more interested in finding bigger differences than smaller differences, and even if smaller differences are statistically significant, we might not care all that much. But figuring out what sort of sample size you might want before running an experiment is more of a way to figure out if you're possibly wasting time and money. And the more complicated the experiment, the more difficult it is to accurately and precisely estimate a reasonable sample size. In my case, I lament my likely loss of being able to achieve such a large sample size. Making sure the experiment's procedure and the questions you are asking are sound could be a more effective way of having powerful tests. For example, if I asked people to rate cookies on a scale of 1 to 10 instead of 1 to 5 stars, I could potentially capture a lot more differences, since a single point on a 10-point scale is roughly half a star, which I would still consider notable. But I digress, for I am not in the mood to make hundreds more cookies, let alone purposely poorly produced ones. On top of finding that many test subjects. I will be in my lab, working on a new creation. That is all. Be gone!